All right, I'll be right back. I'm just going to go pick up your notebooks.
When we did the it's only available. I changed it to so we got the symbol and the A. We can get it. I should have changed it to yeah, so the purchase and everything. Yeah. Yeah. When I go to yeah. Speak for yourself. Yeah, that makes sense. What? That would be really funny, is if down there they had cows that made chocolate milk and we were just doing the yeah. We just came through it. No, they tried to move the chocolate. I will say it was there's like milk chocolate isn't that what in the day? They really make chocolate. I'm just saying. I'm just saying. Maybe we don't know everything. Maybe it's always like that's just what happened. You are the oh, really? All right, so if you want to, I'll give a couple minutes so you can grab your books. I think they're roughly organized by lab section, but not alphabetical as far as I know. So this looks like LO1 is here and LO2 is here. Yeah, LO1 is the morning and LO2 is the afternoon. Oh, yeah, so like. All right. Where are I don't know, you might have done it different than I do. Missing program specs. That's all different. That's. Oh.
Okay, so I hope everybody had a good weekend. So yeah, the books, if you haven't picked yours up, they're up front here. So what we were hoping to do and what we've done is to try to provide some feedback on lab 1 before you have to submit your lab number 2 notebook on Thursday. So take a look at the feedback that you got. If you had any questions, I encourage you to ask the TA first who did the grading. If you're not satisfied with that answer, if you do have anything to ask, then you can come see me after that. Okay, so what I want to do today is I want to do some examples of applying this propagation of errors expression that we came up with last time. And so what I'm going to try to show is that with the exception of one small change, this rule or this propagation of errors formula reproduces all of the rules that you memorized from first year. So let's see how that works. Before we do that, let's remember the way we did this is we started thinking about a function y is f of x that depends only on one variable. And we wanted to know if there was some uncertainty in x, how would that translate to y? Well, the derivative of y with respect to x gives you the slope of a tangent line at whatever point you're interested in. And so in that case, if I vary x a little bit, the variation in y is the slope times delta x. And so that's where these things come from. And then if we had a function that depends on multiple variables, then we would have a term like that for every variable x1, x2, up to xn. The only wrinkle, and the part that's new compared to first year, is that we said that we would have to combine these uncertainties using this quadrature sum. So you're going to square all the individual contributions, add them up, and then take the square root. Okay, so let's see how this works in practice, and we'll start with some easy examples. So today we'll do some examples of propagation of error. And so the first example is, say R is equal to V over I. So in the last lab number 2, you made a bunch of measurements of the voltage and current for a resistor, and then you could calculate, if you wanted to, for each measurement, the resistance as V divided by I. So what we're going to imagine is that we've made measurements of V plus or minus delta V and I plus or minus delta I, and the goal is to try to find the uncertainty in R. Okay, before we actually do this propagation of errors calculation, let's just remember what we would have done in first year. In first year, we would have said, okay, the resistance is the result of some division, a quotient. And so I had a rule for propagating errors when we had quotients. That rule was that the fractional error in R would be equal to the fractional error in the voltage plus the fractional error in the current. Okay, so let's just keep that in our minds, so that after we do our propagation of errors, let's see how it compares to this rule. Okay, so from propagation of errors, well, what do we have to do? We have to say the uncertainty in R is going to be the derivative of R with respect to voltage times the uncertainty in the voltage. So we'll have one contribution because of our uncertainty in the actual absolute value of the voltage. And then we'll have a contribution like that for the current. And then we're going to just apply our quadrature sum. So we square those two terms, add them, and then take the square root. So that's just propagation of errors for our function of two variables. Okay, so let's just evaluate these derivatives. Propagation of errors is always going to work as long as we can do these derivatives that we have to calculate. So R is V divided by I. So what's the derivative of V over I with respect to V? 1 over I, that's right. So we treat, in this case, the current as a constant when we're evaluating this partial derivative, and V is the only variable. So we have V divided by a constant, which is just 1 over the constant. Okay, and then the other one we have to do is the derivative with respect to current. And so this time we treat the voltage as a constant, and we have the derivative of a constant divided by I. So if this was like the derivative of 1 over x, you would right away say that that's going to be minus 1 over x squared. And so instead of an x, we have the current. And then we just have to carry around the voltage factor, which we're treating as a constant for the purposes of the current derivative. Okay, it's going to turn out that for these propagation of error calculations, an overall negative sign in front of a derivative is not going to matter, because ultimately we're always going to square those derivatives. Okay, so this derivative, strictly speaking, is a minus V over I squared, but because we're going to square everything, I don't really care about that overall minus sign up front. All right, and so then we're just going to sub in for our two derivatives and see what we get. So therefore, the uncertainty in the resistance is equal to, let's see, it's going to be the square root of the first derivative, which is just 1 over I. And then we have to multiply by delta V squared. And then we go plus the derivative with respect to current gives a minus V over I squared. I'm not going to write down the minus sign because I know that I'm going to square everything. So I'll just write V over I squared, delta I, and then square it. Okay. So that is the result. So in principle, this is done. We know everything on the right-hand side of this expression. We've made measurements of the current and voltage, so we know V and I. And we've also made estimates of their uncertainty. So we know delta V and we know delta I. And so all of those quantities are known. We just calculate the uncertainty and the resistance. Now, what I wanted to do is I wanted to compare this to the first year rule. And at the moment, it's not really clear that these are related in any way. But one thing I'll notice is that the first year rule calculated the fractional uncertainty in R. So let me calculate delta R over R using our new method here. So to compare to the first year rule, let's find delta R over R. Okay, so I'm just going to divide everything by R. I'll do it slowly. So the left-hand side, we just divide by R, and then I'll put a 1 over R here and square root all of this stuff. So all of this other stuff, I'll just write the same, 1 over I delta V squared plus. For the second term, I'll do one little thing. I have 2 factors of I here. I'll keep 1 over here, so I'll have a V over I, and then I'll take another factor of I, and I'll write it as delta I over I. Okay, so I'm going to write this as V over I delta I over I, right? That's the same thing. Okay. But what's this V over I? R, that's just R, right? So that's exactly what it is. This is just R. Okay. Now, the other thing I'm going to do is, when you looked at the first year rule, we had delta R over R was equal to delta V over V plus delta I over I. We've kind of put in a delta I over I here. So I want to do something similar for the first term. So I'm going to divide by V, and I can do that as long as I multiply by V, right? So V over V is just 1, I can do that. Okay, but if I do that, then I have V over I here. You already told me that that's just R. Okay, so then let's rewrite everything. We have 1 over R square root of, well, let's see. I'm going to have an R squared times delta V over V squared. So we'll have a R squared delta V over V squared plus, well, R squared times delta V over I squared. Squared delta, delta I over I squared. If I said delta V, then that was a mistake. Okay. Now there's a common factor of R squared. It's under a square root sign, so if I took it outside, it would just be a common factor of R, which is going to cancel with this one. And so we can cancel these things. And so therefore, our final result for the fractional error in the resistance is the square root of delta V over V squared plus delta I over I squared. And so what we've managed to do is to show that our propagation of errors results gives the similar answer to the first year rule. The only difference is that it's the first year rule where we apply a quadrature sum to the two terms instead of just adding them directly. So this is like the first year rule, with a quadrature sum. So the takeaway from this example is that what they were really doing in the first year labs, whether it was chemistry or physics or whatever first year lab that had error propagation in it, is they were giving you a set of rules that essentially you were taking the derivative without being told you were taking the derivative. It's essentially what you were doing, okay? So they use this fractional error addition because it works out the same as propagation of errors, except for this quadrature sum. So remember, when you do a quadrature sum, that gives an answer that is less than the direct sum. So delta v over v plus delta I over I is greater than this expression in the square root. And so in first year, without the quadrature sum, you were actually overestimating your uncertainties by a little bit. Okay, so I want to keep going. I want to show you that we can recover a lot of the other first year rules as well. So let's do another example. So y is equal to a x to the power n. A is a constant. Oops. So this is the rule for powers. So in first year, what did they tell you to do? How would you do this in first year? What's the uncertainty in y? Somebody must know. Okay, no volunteers, then we'll just power through then and just calculate this. So let's use propagation of errors then. We'll see if our results will jog any memories. Okay, so propagation of errors says that the uncertainty in y is going to be the derivative of y with respect to your variable. So what we're going to imagine is that we've measured x. So we measure x plus or minus delta x, and we're going to assume that a and n are constants that are known, so we know their values. Okay, so this might be like x squared or something, and the a might be 1/2. So for example, it could be the displacement when you have constant acceleration and you start from rest. So if you drop an object and it falls, its displacement is delta y is minus 1/2 gt squared. And so maybe we're going to measure t. This is 1/2 g, and then n is 2. So we're going to assume. Oh, why isn't this writing? We're going to assume that a and n are constant with no uncertainty. Okay, so it's only our uncertainty in x that we're worried about. So if that's the case, then our propagation of errors says we would first take the derivative with respect to x, then we would multiply by the uncertainty in x, and then we would take the square root of the square of all that. There's no other terms to add because there's no other variables that we've measured. Okay, so dy dx is going to be d by dx of, let's see, a x to the n. All right. A is a constant, so we're just going to get that constant. And then what's the derivative of x to the n with respect to x? That's right. Okay. So that's all of the work. Now we just have to sub this back into our general relationship of propagation of errors. So delta y is equal to the square root of a n x to the n minus 1 is the derivative, and then we just have to multiply by delta x, and then we square it and take the square root. So of course, what happens if I square a quantity and then take the square root? What do I get? I get the absolute value. So I'm going to write this as the absolute value of a n to x to the n minus 1 times delta x. And that's it. The reason that we have to put the absolute value is because in this example where we said the displacement when I drop an object is -1/2 gt squared, in that case, A would be -1/2 g, a negative number, and we want to calculate positive values for our uncertainties. So that's the reason for the absolute value sign. Okay, what I'm going to do is I'm going to do something similar to what we did for the previous example. Let's consider delta y over y. Okay, well, delta y, we just did that calculation. And then y is a x to the n. And I'll just put this all in absolute value signs, just because we're going to want a positive value for this fractional error. And then what do we get? Well, the a's are going to cancel. Then we have x to the n minus 1 divided by x to the n. That's just 1 over x. So all of this stuff is 1 over x. And so what we end up with is n times delta x over x. And that was the first year rule that you were given. If you had a power, the fractional error in y is given by the fractional error in x times that power. And in this case, our answer was exactly equal to this. Because the reason we got the exact answer is because there was no quadrature sum. That's the difference between propagation of errors that we're using now and what you were told in first year. So this one recovers the first year rule exactly because there is no quadrature sum. So this is the first year result. Let's see. Yeah.
If the power was constant, would you still do the propagation of errors?
Yeah, you could. So then you would have to so if n wasn't constant, then you would have to take the derivative. You'd have a term in there that would be take the derivative with respect to n.
Oh, yeah, after you take with respect to x.
Yeah, if you had uncertainty in x and n, then you would have two terms, and then you would do the quadrature sum. So you would take this, you'd square it, and then you would add to that the derivative of y with respect to n times delta n, square it. Yeah, exactly. Okay, let me do an example that highlights why this propagation of errors is a better procedure. We could do addition and subtraction. We would get the same rule, except it would be quadrature sum. And so I encourage you to do that, to give that a try. So let's do another example. Let's suppose that y was equal to x times ln of x, and we know, or it might be better to say that we've measured x plus or minus delta x, and we want to find delta y. So now we have a problem because our first year rules told us how to handle products, and so we could do that, but we weren't given one. It wasn't one of the standard rules for the ln of x. But propagation of errors doesn't care. It says, can you take the derivative of this function? If you can take the derivative, we can evaluate the uncertainty in y. So there's no first year rule, but propagation of errors still works. All we have to do is say delta y is dy dx delta x squared square root. Yeah.
Really just has to exist, right? It need not be constant or need not be continuous.
Yeah, it just has to exist. So if you had a discontinuity, you'd have a problem. Yeah. Yeah. So okay. In this case, what we can do right from the beginning is we can say, look, there's only one term, the square root and the square are gonna cancel. And so we could just from the beginning say that this is going to be the absolute value of this derivative times delta x. Okay, so in fact, I don't even have to write, because it's a function of one variable, we don't even have to write it as a partial derivative. We can just say dy by dx is going to be d by dx of x ln x. So we have to use product rule. We take the derivative of the x, that's a 1, multiplied by ln x. So the first term is just ln x. And then product rule says, okay, write down the first factor, x, and take the derivative of the second factor, ln x. What's the derivative of, ln x? 1 over x, exactly. Good. So then we just get that this dy dx is equal to ln x plus 1. And so therefore, delta y is equal to that derivative times delta x, and stick it in an absolute value sign. Ln x plus 1 delta x. Okay, good. So I want to do one other thing before we kind of leave this uncertainty analysis behind us. Well, not behind us. We basically have finished what we're going to do for uncertainty analysis in this course. So going forward, what I want you to do is when you're in the lab and you're taking measurements of something, when you want to calculate the uncertainty in a quantity that's derived from something you've measured, you should always be applying propagation of errors, okay? And so that's what I'm going to ask the TAs to look for in your notebooks. So is there any other questions about any of this? Yeah.
No, like you can just do propagation of error. They're gonna know what it is. Don't have to list anything as long as they list what's obviously being used in variables.
Yeah, your TAs know about propagation of error. Yeah, they do. Okay, so let's now, there's one thing that we did that we haven't yet justified, and that was the standard error. So the last thing we'll try to do is let's try to justify / derive the standard error in the mean. So remember what we were talking about. We were talking about dropping this coin from the building many times. We do many trials. What should we report as the best result of that whole set of trials? Well, one obvious thing to do would be to report the average as our best estimate of the value. But for the uncertainty in that average, what we said we should use is the so-called standard error sigma mu. And that was just equal to the standard deviation divided by the square root of the number of trials. So this is standard deviation. This is the number of trials. And this is our standard error. Okay, so what I want to do is I want to try to use propagation of errors to see if we can recover this result. Okay, so the strategy is to write down, write down an expression for the mean mu, and then apply propagation of errors. Okay, so we can do that. So mu is just 1 over n times, well, the sum of all of our trials. And I'm going to write it this way, just to make it explicit that we have these n terms in here. And, you know, if we're going to calculate this average, that means we've measured x1 and x2 and x3 all the way up to xn. So we measure x1 plus or minus delta x1, x2 plus or minus delta x2, all the way up to xn plus or minus delta xn. Okay, now we have our propagation of errors formula, which handles exactly this case. So this is now a function of n variables. Okay, so propagation of errors says that, well, the uncertainty in y is going to be the square root of a bunch of stuff. So, so I better write this as the uncertainty in mu. So we have mu is equal to a bunch of stuff. So it's derivative of mu with respect to our first variable x1 times delta x1, plus the derivative of mu with respect to x2 times the uncertainty in x2 squared. And we go all the way up to the nth value of x. Okay, so there it is. So here's the question. What is the derivative of mu with respect to x1? If I take a derivative of this thing with respect to x1 and hold all the other x's constant, treat them as constants, what am I going to get? Not x1 over n, just 1 over n, right? Because I'm taking the derivative with respect to x1. That's exactly right. So it would be, I'll write it out in detail for this one example. So it's going to be 1 over n times x1 plus x2 plus and so on, all the way up to xn. So I can distribute the derivative. N is a constant, it comes out front. And so we would just have a 1 over n dx1 plus dx2 with respect to x1 plus dxn with respect to x1. Okay, but the derivative of x1 with respect to x1 is just 1. And there's no x1 in the second term, so its derivative is 0. And all of the other terms will have a derivative of 0 because there aren't going to be any x1s in any of these terms except for the very first one. And so what we get is just 1 over n. Now you could do this for x2, x3, all the way up to xn. It's always going to be the exact same result. So we could say likewise, d mu dx2 is going to be 1 over n. Whoops. And d mu dx3 is going to be 1 over n. And d mu dxn is going to be 1 over n. All right, so in this expression here, wherever you have these derivatives of mu, it's always just going to be 1 over n. Okay, so therefore, the uncertainty in mu is going to be the square root of these derivatives. So it's going to be a 1 over n delta x1 plus 1 over n delta x2. So let's see. Okay, and then it's plus 1 over n delta xn squared. Now, obviously, we have a 1 over n squared in every single term. We could factor that out. So we'd have 1 over n squared times delta x1 squared plus delta x2 squared, and so on. The 1 over n squared I can take out of the square root as just a 1 over n. And so all of this is equal to 1 over n square root of delta x1 squared plus delta x2 squared plus, and so on, plus delta xn squared. So now the last little bit of insight is that for each of these individual measurements, we expect each measurement, like the collection of measurements will follow a Gaussian distribution. And so typically an individual measurement is expected to be about a standard deviation away from the true mean. And so if we've made a good estimate of these uncertainties in our individual trials, these should all be approximately equal to the standard deviation, right? 68% of our measurements will fall within 1 standard deviation of the mean. Sometimes they'll be closer to the mean, sometimes they'll be farther away, but typically they're about 1 standard deviation away. So typically, each individual measurement is expected to be approximately 1 sigma from mu. Let's say on average. And so therefore, it must be the case that, let me write this over here. So therefore, it must be the case that delta x1 is about equal to delta x2, which is about equal to all the way up to delta xn. And these are all about equal to sigma, or the standard deviation. Okay, so if we make that change, or that substitution, uncertainty in the uncertainty in mu should be equal to our 1 over n out front. And then we have sigma squared plus sigma squared plus sigma squared. How many sigma squared terms do I have? N of them. And so this is going to be 1 over n times the square root of n sigma squared. And so now I have root n divided by n, which is 1 over root n. And then we have a sigma squared square root. And so this is sigma over root n. And so that is the result that we wrote down a few classes ago. And so therefore, the uncertainty in the mean is standard deviation divided by the square root of the number of trials. And this was the results that we wanted to find. Okay, good. So is there any questions about any of these examples? Yeah.
So plus or minus doesn't imply the maximum or minimum possible values that that the actual answer could be. It's the.
No. No, like the Gaussian distribution, the tails go all the way to plus minus infinity. So in principle, it's possible that you could get a measurement that is like 10 times away from the average value. It's just the probability of that happening is extremely small. Like getting a measurement that is three standard deviations away from the mean is like I guess what it was, it like 99.8% of, or 99.9% of your measurements are going to be within plus or minus 3 standard deviations. It's still possible to get measurements outside of that range. It's just that that probability becomes vanishingly small.
So then, what's the purpose of having a plus, like just it's a relative guess, because then you're more uncertain than what you're actually just.
No, I mean, it's what you're saying is that if you're within one standard, if you report your uncertainty as one standard deviation, plus or minus one standard deviation, what you're telling people is that 68% of the time, I expect my measurement to fall within plus or minus this value. But you don't have to do that. So if you were doing a particle physics experiment and you discover a new particle, you wouldn't report that with only a 68% confidence. You would say, I'm confident to within, they do something like 5 sigma. And so there's a 1 in a million chance that this is a statistical fluctuation and what we discovered is not actually a real particle. So what you have to tell people is, what is your confidence interval? Is it 1 sigma, 2 sigma, 3 sigma, 5 sigma? Typically, we're going to use 1 sigma, and that implies 68% of the time our measurements fall within 1 sigma of that measurement. Okay, so I think I wanted to do one other thing, and that was, how are we doing time-wise? Okay. Oh, so we have like 7 minutes left. So what I wanted to do was to talk about the experiment that you're going to do on Thursday. So this will be like a lab 3 preview. What we're going to do in lab 3 is you're going to measure a RC circuit. So we talked about, we solved that differential equation that describes the RC circuit. And so remember, if we had to charge a capacitor through a resistor, we would have something like this. We would have, say, some DC voltage, like a battery, maybe a switch, and then we have our resistor, and then we have our capacitor, something like this. And maybe we're going to measure the voltage across this capacitor. Here's the capacitor voltage as a function of time. So if we close the switch at t = 0, then the voltage across the capacitor we calculated to be V naught 1 minus E minus T over tau, where tau was equal to this RC. So it's some time constant. All right. So that's fair enough. And we could plot that. And so if this is time and this is your capacitor voltage, it's going to start at 0. And after a long time, after maybe 3 or 4 or 5 time constants, it'll reach its final charge, which is V naught. And the evolution or the approach to that final charge looks something like this. Okay, now we could have done the other opposite problem. We didn't do it, but we could have. We could have said, let's start with the switch closed for a long time. We'll let our capacitor fully charge. And then what we can do is we could try, here, let me modify, let me do a better version of this picture. So we'll put a ground here. And so this is a better version, S. So in this picture, we start with the switch down and then we flip it up and we charge it. We could start with the switch up, capacitor fully charges, and then we flip the switch down so that it would discharge through the resistor. If we analyze that case, we would see the following. So discharging a capacitor through resistor R. Okay, so the capacitor is initially charged to V naught, and then we flip the switch down. Flip switch down at t equals 0. If we analyze that case, we would see that the capacitor voltage as a function of time is going to be V naught E minus T over tau. And tau is the same product of R and C. All right. And if we plotted that case, what we would do is we would see our capacitor voltage would start at V naught. And then it's just an exponential decay. And an exponential decay looks something like this. So this shouldn't be rising up. It sits at 0. So in the lab, what you're going to do is we're not going to use like the mechanical switch that you actually flip up and down. What we're going to do is we're going to use the TTL output of the function generator, which outputs the square wave, 0 to 5 volt square wave. And when the output of that square wave is high, it's like the battery's in the circuit. So that's the switch is flipped up and our capacitor charges. And then when the square wave goes to 0, it's like we took the battery out. And so the capacitor discharges and we see an exponential decay. So this will be the last thing I write down. In the lab, we will use the square wave to simulate a switch. So let me just plot for you what that would look like. T, and then this is, say, the output of the square wave generator. And then we'll plot over here the corresponding voltage of our capacitor. So our square wave is going to go to some positive to 0, positive to 0, back to positive, and so on. And there's going to be some important times, and those times correspond to the transitions of the square wave. And so we would have charging, discharging, and then charging, discharging, charging, discharging. And so what our capacitor would be doing is it would charge up, reach some maximum. Then when the square wave goes to 0, it'll discharge, and it'll just repeat this process over and over again. And we're going to investigate these waveforms on the oscilloscope, and we're going to make a measurement to try to determine the RC time constant of the circuits that we analyze. Yeah.
Does it mean we want the square wave for a really large period?
Yeah, that's exactly what it means. So it means that we want this time. So this time would be half a period, right? We want this time to be long enough so that our capacitor fully charges and then fully discharges. So what we have on your function generator is a little knob to set the frequency. To increase the period, like if it's not charging up or discharging enough, you lower the frequency so that you increase the period of the square wave. Okay, so we'll finish discussing this preview of lab 3 on Wednesday. and then we'll move on to a new topic. If you haven't already done so, the lab books from lab one, grade lab books from lab one are up front here. Okay.